In these next couple of videos, we're going to talk about the problem of quantum teleportation and then how to carry out quantum teleportation. Let's get started. So let's imagine that Alice has managed to create a wonderful qubit in her lab. And what she wants to do is analyze the qubit. So she doesn't know what the qubit looks like. So it's alpha 0 plus beta 1, but she doesn't know alpha and beta. And she wants to transport this qubit to Bob's lab. But Bob's lab is far away. They don't have a quantum channel between them, a way of transporting quantum information. Now, of course, it's a very bad idea for Alice to measure her qubit to try to figure out alpha and beta, because if she does so, she'll destroy the qubit, the superposition, and she'll learn very little information about alpha and beta. So how can she possibly transport this qubit to Bob's lab? So the answer is quantum teleportation. So let's assume that Alice and Bob share a Bell state. So Alice has a qubit and Bob has a qubit, which are entangled in the state 0, 0 plus 1, 1. So now quantum teleportation is a protocol by which Alice performs some measurement. So she performs some measurement on these two qubits. On her qubit, the unknown qubit that she wants to transport to Bob, and her share of the Bell state. So she measures these two qubits and gets two bits as B1 and B2. This is the result of the measurement. Now, in the process, it seems as though her qubit has been destroyed. But what she does now is she picks up the phone and calls up Bob and tells him what these two qubits are, these two classical bits are, B1 and B2. So maybe B1 equal to 0 and B2 equal to 1. So she calls up Bob and she tells him 0, 1. Now, based on what Alice told him, Bob performs one of 4 different quantum gates on his qubit. And after having transformed his qubit, so he puts his qubit through one of four gates, which depend upon, the choice of the gate depends upon what Alice told him. And the output of this gate, lo and behold, is guaranteed to be alpha 0 plus beta 1. So this is the magic of teleportation. So what Alice does is she has this unknown quantum state. She wants to transport it to Bob. And so in the course of teleportation, she destroys her qubit. She has to call up Bob and tell him 2 classical bits of information. And in the process, she allows Bob to reconstruct her qubit. Now, of course, you might be puzzled by all this because there were 2 complex numbers here, alpha and beta. How did they get transported to Bob? You'll see the protocol. You can try to puzzle over this once we do that. Okay, so we are going to look at this quantum teleportation protocol in 2 steps. We are going to understand it in 2 steps to simplify it. So first, I'm going to assume something unrealistic. So I'm going to assume that here's Bob's qubit. It's initially 0. So I'm going to assume Alice had a qubit, alpha 0 plus beta 1. Bob, in his lab, had a qubit that was initialized to 0. And I'm going to assume that there's a C0 gate that extends from Alice's lab to Bob's lab. Of course, this is completely unrealistic, but this is a stepping stone to the quantum teleportation protocol. Okay, so Alice applies a C0 to Bob's qubit using her qubit as a control bit. And so what's the result? Well, you get alpha times 0, 0. And then, so what's the input? The input is alpha 0, 0 plus beta 1, 0. And now what does the C0 gate do? Well, it leaves 0, 0 alone. But 1, 0, when the control bit is 1, it transforms it to the target bit. So it becomes 1, 1. Okay, so now we have these two qubits entangled. You have the entangled state alpha 0, 0 plus beta 1, 1. Now, is there something that Alice can do so that Bob ends up? So you see, what we want is that we should end up with this qubit, with Bob's qubit. We want it to end up in the state alpha 0 plus beta 1. So the question is, what should Alice do? Now, one thing you might think is, well, maybe what Alice should do is measure her qubit. And let's see, how should she measure her qubit? Well, she might measure it in the 0, 1 basis. And so if she sees 0, the new state is 0, 0. If she sees 1, the new state is 1, 1. This is no good, because in either case, Bob ends up with either the state 0 or the state 1, which looks nothing at all like this state that he wants to end up with. So that's not a good idea. Here's a better idea. What if she measures in the plus minus spaces? Okay, let's try to understand what this gives us. So to figure this out, we first rewrite the joint state of the two qubits, where we rewrite the first qubit in the plus minus spaces. So this is alpha times, what's 0? It's 1 over square root 2 plus 1 over square root 2 minus tensor 0 plus beta, what's 1? It's 1 over square root 2 0 minus 1 over square root 2 1 1. So remember that we either write the tensor sign or we drop it according to convention. It's sort of depending upon how lazy we want to be. Sorry, I made a mistake here. This was, we wanted to say 1 is 1 over square root 2 plus minus 1 over square root 2 minus. And now if we collect terms and we say, well, this is 1 over square root 2 plus times alpha 0, so you got plus here and plus here, plus beta 1 plus 1 over square root 2 minus, and we got alpha 0, and then you got minus beta 1. So what's this telling us? So if Alice measures her qubit in the plus minus basis, then if she measures plus, then the new state, so the new state is equal to plus alpha 0 plus beta 1. And if she measures minus, then the new state is minus alpha 0 minus beta 1. Okay, so in the first case, what's the state of the second qubit? So you can see that this is a tensor product state, meaning that the first qubit is in the state plus, and the second qubit, Bob's qubit, is in alpha 0 plus beta 1. This is exactly psi, which is what we wanted. What about in this case? If she measures a minus, Bob's qubit is in the state alpha 0 minus beta 1, which is not the same as psi. But what we do know is that if you apply a certain gate to it, you can convert it into psi. So which gate would you apply? Well, you want to change this phase from minus to plus. How do you do that? Well, you apply the phase gate, Z, right? The phase flip gate. So Z times alpha 0 plus beta 1, sorry, Z times the state alpha 0 minus beta 1 is equal to psi. So what Alice should do is measure her state in the plus minus basis, and then if the result is plus, she transmits. If plus, then she transmits to Bob a bit saying 0. If she gets a minus, she transmits to him a bit saying 1. So she calls him up, says 0 or 1, I got a plus or I got a minus. If Bob hears 0, he leaves his qubit alone. It's already in the state phi. If he hears 1, he says, aha, I got alpha 0 minus beta 1. So I'm going to apply a phase flip gate to my qubit, and I'll now have my qubit in the state psi. So this shows how Alice can transmit her qubit to Bob if there was a C0 gate that stretched between her lab and Bob's lab. Of course, this is completely unrealistic. So in the next video, we are going to try to understand how to deal with this challenge. How to create this entangled state alpha 0, 0 plus beta 1, 1 without quantum communication between Alice and Bob, or without this quantum gate that stretches between Alice and Bob's lab.